Hi, Bobby.
Hi, Anirudhan.
So what do you want to do today?
Actually, we discuss about resistor, capacitor, inductor,
Correct.
and sinusoidal excitation, various kinds of excitation. But let's say when you give sine wave, I wanted to process only the positive half cycles. Can I achieve that using these elements?
That's interesting. Okay, so maybe what I will do, I'll start by drawing. The sinusoid.
Our Vm sin omega t.
Vm sin omega t. So let us say Vm minus Vm. Okay, and you want to?
I want to have some non-linear operation.
Okay, so what you said you wanted to do only the positive.
Yes.
And what happens during the negative?
I want to just cut off those.
Oh, I see.
Yeah.
Okay, so if I draw it like this,
yeah.
Is it correct?
Yeah.
Oh, okay.
So that becomes kind of a non-linear operation. No?
Definitely, because it looks like at least for t for this time.
Yeah.
The output and input are completely unrelated. No?
Correct, correct.
So it is
correct.
zero. It doesn't matter what minus Vm
correct,
is.
Correct.
So it's definitely non-linear. Okay.
So with RLC,
yes,
we don't see this happening.
We don't see this happening for sure. So I'm going to draw that separately by itself. So V prime of t. So you are saying you want just this.
Yes.
Oh, okay. Yeah, definitely you need non-linear, right? Because we are used to some, let's say, resistor. For all time, the current and voltage are related, and so on.
The other ones are only introducing phase shift.
Phase shift, right? Okay.
Or change in impedance with respect to frequency, etc. But not true. This kind of operation.
That is true. So most likely, well, we know this, right? These are the three components that we know.
Yeah.
R, L, and C.
Yeah.
And as you rightly pointed out, none of these elements will give us this.
Correct.
Well, these are all electrical elements. We need to go to electronics. Right? Actually, our title of the course has that.
Okay.
So I think we are going to enter another interesting phase of the course.
Nice.
And I think, as you rightly pointed out, I think a lot of electronics uses nonlinear behavior, isn't it? So let's look at some very simple. We had two terminals, no, for each of these.
Correct. So we are going to have more terminals.
Let's start with two. Maybe later.
Okay.
Let's start only with two.
Okay.
So let's start with two terminals. So maybe I'll just show like this. Some unknown element, right? I don't know what it is. I have two terminals A and B, and I want it to behave differently, no?
Correct.
For positive.
I wanted to basically I wanted to have a closed switch.
Closed switch
for positive.
For positive, open switch in negative.
Correct.
Okay. So if I were to actually, so interestingly, if I were to draw the IV characteristics, I'm going to draw I versus V. Right? So I have a current I and I have a voltage V.
So voltage across the device and current through the device.
So let's do it for a resistor first, and then we'll compare with that. C and D, I have a resistor R.
Yeah.
And let's say this current was IR.
Yeah.
And the voltage was VR. If I were to plot that here, plot the IV characteristic. So I'll use a different color for the resistor.
Same color.
Same color is fine.
Yeah.
So I'm just going to draw the resistor first. We know that it does something like this.
Yeah.
And the slope of this is 1 over R because I'm drawing I versus V. So I is V by R.
Correct.
So slope is 1 over R.
Correct.
And I can, if I choose a different resistor, I'll get smaller or larger slope. And I noticed something very interesting. the behavior for negative voltages and positive voltages is the same.
Same.
Right?
Slope is not changing.
Slope is not changing. What you are now telling me,
Hmm.
you want this device,
Hmm.
some unknown device.
Yeah.
You want different behavior in this region
Correct.
and different behavior in this region.
Correct.
Right?
Correct.
And you said switch. No,
Yeah.
it should look like a switch.
Yeah. So for that kind of waveform to get,
Yes. So
if we have a switch.
if you have a switch, let's draw that.
Yeah.
I want a closed switch in this region.
Yeah.
And I want an open switch in this region.
Correct.
Right?
So in the first quadrant,
So it should look like this.
Yeah.
So in the first quadrant, a closed switch will have
Exactly.
any current, no voltage.
yeah, or any voltage more than zero,
More than
current can be anything.
Current can be anything. Correct?
Hmm.
And I'm guessing you would be happy even if you got a straight line like this. You may also be happy with that.
Somewhat.
Somewhat. But you would want this to be zero, I guess.
Yeah, ideally.
Right? Ideally zero.
Yeah,
Okay. Because you wanted to reproduce the sinusoid perfectly.
correct.
Right?
Correct.
Okay. So let us draw this like this. Now here you want it to look like an open switch.
Yeah.
Oh, then
That
no.
means for any negative voltage, current is zero.
Current is zero.
Yeah.
So we want an IV characteristic like this.
Yeah.
Okay. So this is your unknown device.
Hmm.
I understand now. Well, we need to go to the electronics textbook.
And see whether something satisfies this.
Something satisfies this.
Hmm.
And it turns out there is such a device.
What
Okay.
is that?
It starts with a D,
Okay.
ends with an E.
Oh.
I think most students would have studied it in high school now, right?
Yeah, in the 10th standard, I remember.
Okay. So,
Diode?
Diode, that's right.
Yeah.
So this device, such a device, which gives very similar characteristic is called a diode. And
Or an ideal diode will give this.
ideal diode will give this. Okay.
Mm-hmm.
So I'll add that here.
Yeah.
Right.
Yeah.
Ideal diode will give this characteristic. A real diode may look slightly different.
Then what is this real diode?
So first step,
Hmm.
maybe what we'll do is we'll show them the symbol for the diode. We'll start with that.
Yeah.
Because they need, just like when we started doing resistors, inductors,
Correct,
first
correct.
thing we did was draw the symbol.
Correct.
So maybe we'll do that here.
Hmm.
Okay. So just give me 1 minute. I will change this also to the right color so that everything is consistent.
Yeah.
Okay. Now we are going to talk about the diode. So this is the symbol for the diode. It's
Okay.
quite different from RLC. We used very simple figures.
Yeah.
This is now becoming more geometric.
That figure itself is becoming nonlinear.
That's right. So one thing about RLC is that like you said, they represent many things. Like L, you're coiling a wire,
Yeah.
so it shows that.
Correct.
Right. C, for example, it's pair of plates.
Yeah.
It shows that.
Resistor shows some kind of heating effect.
Some kind of heating effect. This one, it looks very different.
Yeah, it indicates something.
It indicates something. So there is an arrow that is showing us something. So this portion is showing us that the current flow will be from left to right.
Only in that direction.
Only in that direction. That's what we wanted. So this, now because it's a diode, so this is a real diode, no?
Yeah. Not the ideal diode.
Not the ideal diode.
Okay.
Well, this is, you have an ideal diode symbol and a real diode symbol.
Yeah.
We will just use the same thing.
Yeah.
I think we don't want to confuse beyond a certain point.
Correct.
So maybe we will say it's a real diode.
Yeah.
And we will call this current ID.
The current through the diode.
Current through the diode. And we will say that the voltage across the diode is VD.
VD.
Okay. And some, I'll just name these for consistency's sake, some E and F.
Nodes.
Yeah. So this diode has two terminals, E and F. Normally, the current, if there is current flow, you expect it to flow from E to F.
Okay.
And the voltage drop to be from E to F.
Okay.
This is what you hope will happen.
Mm-hmm.
And this terminal E is called the anode of the diode. And this terminal F is called the cathode.
Mm-hmm.
Oh.
What is this made of? Because RLC, we know resistor is a resistive material, L is some copper or aluminum insulated.
Correct.
Capacitor, two plates insulated.
Easy, no?
This is.
Let us go into that quickly, very briefly, right?
Yeah.
Because they will learn more about this in an electronic devices course.
Yeah.
So maybe we'll spend a few minutes.
Yeah. Just to know what it is.
Just to know what it is. So I think the first thing we need to know is there is a whole branch of electronics that in modern times originated based on semiconductors. Electronics was there before in different ways.
Semiconductor.
Semiconductor. I think that itself gives us a clue.
So it's not a full conductor.
That's right. So it conducts less than a real conductor. You are expected to, like if you take a piece of metal, right? If you take a copper wire, you expect the resistance to be very low.
Correct.
Conductivity to be very high.
Yeah.
This one is not as high as that.
So it's not pure conductor, not pure insulator also.
That's right. So if the resistivity, if I were to, so maybe I'll just, if I talk about the resistivity, so of
rho,
correct, resistivity of the semiconductor, you could say that the resistivity is going to be higher than a conductor.
Yeah.
But much lower than a insulator.
Okay.
Probably it is going to be closer to the conductor than the insulator. Most likely. Because insulator, the resistivity is very high. You almost want no current to pass through. Typically in the semiconductor, you may want, depending on the application, you may want currents to flow through.
So this conductivity, can I change by some way?
Okay, very good question. That depends on how you build the device. So one common way of building this device is to first of all, you build this semiconductor by taking, so you can control it. So first thing to do is to start with something in the periodic table. So metals normally have lots of free electrons
in the valence band.
In the valence band.
Okay.
So if you do that, if you choose a material that has a lot of valence band
free electron,
that's
anyway
it will become a conductor.
Correct.
Right. So we don't want that, and you don't want to choose something where there are no valence electrons also.
Correct.
Right. So you probably choose somewhere in between. So the center of the periodic table.
Okay.
So typically the most commonly used element is silicon.
Silicon.
Yes. But you can also use other
germanium.
And these are the two most common. Silicon is most common, germanium. But silicon by itself is not going to conduct.
Yeah.
Right? So what do you think we should do?
So can I add some impurity
to it? That's exactly what is done. So suppose I take a piece of silicon. So silicon by itself is not very conductive. But then you try to add some impurity, right? So now, normally I'll show like this: electrons and holes, right? The big circle is holes where you have a space for an electron to fill, and the small dot are electrons.
Okay.
So silicon by itself has no, it's not very conductive. But what I'm going to do, I'm going to add some, let me say, some material with some free spaces.
Okay.
Where electrons can go. Then what can happen is this electrons can move between these two.
So what kind of material is that? So, means this will be in their valence band, how it will look like?
Their valence band needs to have a free space. So it needs to be fewer number of electrons than silicon, right? So
maybe I will learn more about this in the devices.
Course. Correct. So maybe we will take one common material just to the left. So we said silicon, germanium, they're in the center.
Yeah.
We will take one element to the left. So one of the easily available elements is boron.
Boron.
So we will take boron. So if you take boron, small amount, not too much.
Yeah.
Then it just becomes not silicon, but
small means it will be very, very small.
Very, very small.
Okay.
Right? Yeah, correct. It's not like,
adding 1 spoon of.
It's not like 1 spoon, not like that. And it's not like it is going to be like half of this area is going to be taken, much smaller than that. And then you can, depending on how much boron you add, you now have ability for making a better conductor.
So there is some process.
There is some process
to do this.
Correct. Again, students will learn about it when they learn semiconductors.
Yeah.
Similarly, you can also take the same type of silicon, but instead of adding,
so the boron will create
what are called holes.
Okay.
Correct.
Okay.
And the minute you do this, you will basically have ability for electrons to move, and you will have free spaces. So you will get what is called a p-type semiconductor.
Okay.
Similarly, I can go move on the periodic table one to the right. Right. So if I take the silicon,
pentavalent also.
Correct. Pentavalent. Correct. So if silicon has 4 electrons, you need to take pentavalent element. I'll show that in a different color. So sorry. So that one will have extra electrons.
Okay.
Apart from, it will have free electrons.
Okay.
And those free electrons, can displace these electrons. So now these electrons will now become free.
Okay.
So
adding this impurity, that process is called doping.
Doping. That is correct. I'll just finish this.
Yeah.
This will be phosphorus, let us say.
Yeah.
And this will give you N-type.
Okay.
Because you have more number of electrons. So if you add boron or phosphorus, this process is called doping.
Okay. So if you dope with boron, we get a p-type.
P-type.
If it's doping with pentavalent, then
it will become N-type.
N-type.
That's right.
So N-type has some free electrons.
N-type has some free electrons.
The other one has some
free holes. We call them holes because there are no electrons there. So electrons can fill the hole.
Okay. So basically some current flow can happen.
Current flow can happen in either way. So in the case of boron, electrons from silicon can go into the free spaces in boron. In the case of phosphorus, electrons from phosphorus can displace the electrons in silicon. Now, I am going to do something interesting. I want to build this device. Let us go back to what we want.
Correct. Yeah.
Any guesses how I can build the device that I want?
I don't know. Only in the symbol I see, there is a triangular shape and then another line. So,
another line. Correct.
So, looks like there are 2 things, but I don't know.
Okay. So, one common way is to take a piece of p-type and a piece of n-type. I'm just showing a representative diagram. It is not a piece of right?
Yeah.
It is a 3-dimensional structure built in a very specific way. But you can take a p-type and an n-type material and put it together to create a 2-terminal device. If you just take only p-type or only n-type, that will have some characteristic with some resistance which will be that of the semiconductor. It doesn't do anything special.
That will not give the half cycle.
It will not give the half cycle that we want, right? But if you do something like this, it does something very interesting. Okay. And again, you can, at the device level, you can calculate things like electric fields, what will happen to the electrons.
So, electric field at the junction?
At the junction, correct. So, this is the junction.
Okay.
Yeah. So,
I heard about forward bias, reverse bias, etc.
Correct. So, maybe we'll move back to this diode because now we have something which approximately, you have a 2-terminal device which happens to be nonlinear. So, this is actually a PN junction diode. And if you apply a positive voltage like this, then current can flow.
Oh, as per the that symbol.
As per
that
the
symbol also will keep here.
That symbol also will keep here.
Okay, okay. So if anode is positive compared to cathode.
Correct. If anode is positive compared to cathode, current can flow.
Ah, okay, okay.
And if
so that's the forward.
That is the forward bias. Correct. So this would be forward bias. I'll just add it here. So this is actually called forward bias. So where current can flow. In fact, we will mark it here also. We have this here. So this portion is called forward bias.
Okay.
So in fact, I can add it here.
Yeah.
And when you want it to behave like an open switch, this is called reverse bias. Because it's not forward, it has to be reverse, no?
So
car goes in forward or car goes in reverse.
Correct. So the voltage will be flipped in the reverse.
Voltage will be flipped because voltage is negative, current is also negative. Current direction also turns negative, right? So that also we will show in the in a different color. I'll choose this color. So if you apply a voltage like this, of course you want no current, but we can represent it like this. This will be the third quadrant. This will be this region of operation for a resistor.
Open switch.
Open switch. In that case, it is an open switch. Same way here.
Not for resistor, diode.
For the diode. If it was a resistor, it will be in the third quadrant.
Correct.
If it is a diode, it's just on the x-axis. Correct.
So we will write reverse bias in that color?
In that color, we will write reverse bias.
So this behavior of this junction, is it very similar to switch or?
It is very close. Some small differences are there. So what we will do, we don't want to go into the device level and study everything.
Correct.
We know voltage and current.
Yeah.
We should just study in terms of that.
That is, I think, for the circuit analysis.
Correct.
Understanding, I am happy with that.
You are happy with it.
Yes,
okay.
Yes.
So then let's just do that.
Yeah.